Hello, everybody. We're going to go ahead and get started today with our first astrobiology seminar of the quarter. If you don't know me, I'm Rory Barnes. I'm going to be the organizer for this quarter. Want to really give a special thanks to Miles and Jim today because they've stepped in on short notice because there was an illness with one of the speakers who was currently scheduled for today. The talks that were normally scheduled here for today are going to be moved to November 7th, so you still get to hear from Andrew and Pete just later in the quarter. So we're gonna, since we have two today, we're gonna have about 30 minutes per speaker. That includes time for questions. So first up is Miles Currie, who is a graduate student here in astronomy, working with Vicki Meadows, and he's going to be telling us today about some recent research that he has just published on detecting oxygen. And so with that, I'm going to just turn it over to you, and please take it away.
All right, great. Thank you, Rory. Can everybody hear me in the back and all that? And people online? There's nobody online? Okay. So as Rory said, I'm Miles Currie. I'm a grad student here in the astronomy department. And I work with Vicki Meadows on this project that I published a few months ago titled There's More to Life Than O2, Assessing the Detectability of Biosignatures in Environmental Context for High-Resolution Spectroscopy of Terrestrial Exoplanets. And I know that was a mouthful, so I'm going to break that down hopefully in the next few slides for you. Oops. Okay, so for this talk, I just want to focus in on transiting terrestrial exoplanets. Keep in mind that probably the best transiting targets that we have right now are in the TRAPPIST-1 system, which is about 12 parsecs away, and it has about 7 planets that we could potentially characterize that are Earth-sized. So unless we find a closer transiting terrestrial planet, this method's mainly going to be applicable to the TRAPPIST-1 system. There are, however, some closer non-transiting planets, but I'm saving those for another paper and another talk. So with that in mind, I'm going to present some optimistic results for what we might be able to do with transiting planets with the ELTs, along with some of the challenges that we're going to have to overcome if we want to study terrestrial planets in transit with the ELTs. So I'm going to start with a few definitions because I know we do have a diverse audience here. Not everybody's an astronomer, not everybody thinks about stars a lot. So the type of star I'm going to be considering for this study is the M dwarf class of stars. These are small, cool stars, and because they're so small and not as luminous as a sun-like star, they're easier to deal with when we're trying to characterize the planets that orbit them, at least to first order. For example, if you had a sun-like star, it could be so bright that it could drown out your planetary signal. So for now, we're going to be focusing in on these small stars here. And the types of planets that I'm interested in for this study are terrestrial exoplanets, which is basically just a catch-all term for small, rocky, Earth-sized exoplanets. However, these don't necessarily have to have Earth-like environments. So in this talk, I'm going to talk about 4 different types of terrestrial exoplanets, and I'll get into each of these 4 in a little bit here. And I don't think I have to convince this group of this, but just to frame the talk, I want to introduce O2 as a possible biosignature gas. So on Earth, O2 is the result of the development of oxygenic photosynthesis, and really life is what helps shape our atmosphere into what it is today. So this is something that people are going to be looking for in this era of searching for signs of life on exoplanets. However, as it turns out, JWST will not have the sensitivity to look for O2 in exoplanet atmospheres. So in the near term, we have to find a different way to search for O2. And that's where the ELTs come in. So ELT stands for Extremely Large Telescope. And these are pretty massive telescopes that are going to be coming online in the next 10 years or so. Their primary mirrors are going to be 30 to 40 meters in diameter. So I think probably bigger than the room. So these are going to be absolutely massive telescopes. And they can do both planets in transmission and planets in reflected light, meaning that it can do both transiting planets and non-transiting planets, which is kind of the novelty with the ELTs, at least in the near term, for Earth-like planets, that is. And finally, the ELTs may be our only hope for near-term O2 searches, and I'm going to get into that in the next few slides here. So as I said, within the next decade, these ELTs are going to come online. These telescopes are going to give us sort of an unprecedented opportunity to study exoplanet atmospheres in detail from the ground. And there have been several studies that have come before mine looking into how well the ELTs are going to be able to search for habitability and life on terrestrial exoplanets orbiting M-dwarf stars. And specifically, these studies have considered O2 in Earth twin atmospheres, meaning exact copies of Earth's atmosphere orbiting M-dwarf stars. And a lot of these studies agree that it's likely going to take between 20 and 50 observed transits to detect O2 on nearby exoplanets. However, there was a recent paper by Kevin Hardy-Ullman saying that it may be more difficult than these initial studies anticipated, but I did not include that one in there on this slide today. But getting back to these studies, they really only consider Earth twin atmospheres, but in reality, we're likely going to find a range of terrestrial atmosphere types out there, and an exact copy of Earth is pretty unlikely. So in this study, I consider 4 different atmosphere types, including some with and some without life. But this is by no means a comprehensive list of all the possible atmospheres we could potentially discover out there. So the ones that host life on this list include a pre-industrial Earth-like atmosphere, which has biological O2, and then an Archean Earth-like atmosphere that hosts life but has little to no O2. And then the other 2 atmospheres here are examples of habitable but uninhabited planets. And here I present them as ocean loss and CO2-rich type planets. These 2 abiotic worlds do have O2 production in the form of water or CO2 photolysis. And they actually are able to build up detectable levels of O2 in their atmospheres. So this is where we have to start being careful about using O2 as a biosignature. And we're going to need to look at the atmosphere as a whole if we want to say anything or something about the possibility of life in that atmosphere. So other molecules are needed to put O2 in context. So in this work, I not only look into the detectability of O2, but all of these other molecules as well that can either enhance O2 as a biosignature gas or indicate that maybe the O2 came from an abiotic mechanism. So the overall driving question for this work is, will the ELTs be able to detect molecules that can provide context to an O2 detection? So an ELT observing strategy is needed for this. We have to figure out whether these other molecules are detectable, the optimal way to observe them. And once we detect them, we have to figure out how we're going to use them to characterize the environment. So what I'm doing in this project is developing an overarching observing strategy for when these ELTs come online. Another thing I'm considering in this work is the effect of different host stars on the detectability of molecules in the atmospheres of these terrestrial planets. So as we know, M-dwarf stars are not all the same. There's actually a wide variety of subtypes that we lump into the M-dwarf category. And an early type M star can actually be quite different than a late type M star in terms of luminosity, spectral energy distribution, size, etc. So planets orbiting these M-dwarf stars may see boosts of important biosignature gases like methane that I've circled here. And this shows up in planetary spectra. So depending on, like I said, depending on which type of a star a planet's orbiting, some of these key gases can change in abundance pretty significantly, like methane, which this plot is showing. So this plot is showing you an Earth orbiting the sun in blue, and then an Earth orbiting an M-dwarf, Proxima in this case, in green. And you can see that just by placing the Earth around the M-dwarf, you can get enhancements in a lot of these spectral features, including methane. So these methane features are a lot more prominent and more spiky, and maybe easier to detect because of that. So again, these are my motivating questions. I'm not going to read them off again, but I just wanted to remind you of those. So to answer these questions with the ELTs is not going to be very straightforward. Since these telescopes are ground-based, we have to answer the question, how do we search for an Earth-like atmosphere while we're looking through our own atmosphere, which happens to be Earth-like as well. So our own atmosphere contains the molecules we want to look for in these exoplanet atmospheres. And untangling our atmosphere from observations of an Earth-like exoplanet can be pretty challenging. So the answer to tackling this lies in using ELT instruments that are going to be capable of high-resolution spectroscopy. So if you're observing a planet transiting a star, the system has some intrinsic radial velocity that's going to Doppler shift the planet's spectrum slightly away from the Earth's telluric lines. And this allows us to detangle the planet spectrum from Earth's atmosphere. And I have a visualization for this in a few slides that I'll show you. Okay, so to answer all my motivating questions, I'm just going to present my methods pipeline real quick. So what I have to do is I simulate ELT observations and use high-res cross-correlation spectroscopy to attempt to detect all of the molecules that I'm interested in detecting in these atmospheres. And the reason we use high resolution spectroscopy again is it allows us to leverage the Doppler motion of the exoplanet to detangle its spectral lines from our own telluric spectral lines. So the first step in this process is to generate high resolution spectra of these atmospheres, which I've done here, and I'm showing you an example of what a noiseless high-res spectrum looks like in the top of the slide. This is the O2A band, if you're curious. And then, yeah, in the bottom of the slide, I'm just showing all the atmosphere types that I'm considering here. Most of these do have oxygen in them. So the next step in my methods pipeline is that I simulate noise and I add it to the noiseless spectrum. So in this work, I'm considering noise from the telescope, the instrument, the detector, the sky, the star, etc. And I created a noise simulator for all of this so that I can pass in a noiseless spectrum and then out pops a noised up spectrum at the end, like the one you're seeing here. And then the next step is sort of where the magic happens. So I take this noisy spectrum and then I convolve it with a template spectrum containing features from only the molecule that I'm interested in. And here I'm showing the template spectrum in red, and it's going across the observed spectrum there. So yeah, as the template spectrum slides across the noisy spectrum, I calculate a cross correlation function, which is showing up in the bottom panel of the slide. And the idea behind this process is that when the features in the template spectrum align with the features in the noisy spectrum, the two are correlated, and you get a detection. So in the bottom panel here, a detection happens at 0 kilometers per second and shows up as the largest spike in the cross correlation function in the bottom panel there. So from this peak, you can calculate a detection significance by comparing the peak to the off-peak values. So these detection significances are what I'm going to be presenting in the next few slides as my results. So without further ado, here are my key results showing how detectable major gases are in different exoplanet atmospheres. And the y-axis here is the number of observed transits it would take to get to a 3 sigma detection. And then the x-axis is all of the different atmospheres I tested, which I also have in the bottom of the slide here. And then the panels of this plot are different molecular bands that I tested. And I also calculated the detection significances for these atmospheres orbiting several different M-dwarf types, which are the different colors in this plot, and the key is on the right side of this plot here. So before I move on, I just wanted to say that all results presented here are observations using the 39-meter European ELT with an R of 100,000 spectrometer for systems 12 parsecs away from Earth. So this is the TRAPPIST-1 system. But if you're curious about other telescopes or other resolutions, feel free to check out my paper, which I'll have a link to at the end here. So for these next few slides, I want to dive into this plot and sort of discuss some of the panels because there's a lot of information packed in here. So first, I want to look at CO2 and methane. These are the most detectable gases with the ELTs that I found. And it's going to take about 10 transits or less to detect these. And this is pretty important because a detection of CO2 can help you rule out larger H2-dominated atmospheres by possibly indicating that the atmosphere is the result of planetary outgassing rather than accretion during formation. So it helps you kind of rule out primary atmospheres. And then methane is also pretty important to detect because, well, first off, it can be detected in even fewer transits than CO2 if the molecule is present in the atmosphere. And the significance of this is that if you were to detect CO2 and methane together, this would constitute a biosignature pair. So just by spending 10 transits on this, you're getting a lot of information out of the atmosphere. So next, I want to take a look at O2. So O2 is detectable in about 30 to 100 transits. And this goes for planets with and without life. So even these planets that don't have biological O2, that O2 is still detectable and just as detectable as the scenarios that contain biological life. So this is where we have to start being careful about where the O2 is coming from in the atmosphere. So this does largely agree with the results of previous papers, but this may be a little bit more on the pessimistic side than the work that came before mine. So another thing I want to note here is that the near-infrared O2 bands, that one at 1.27 microns that I'm circling there, is a lot more detectable than the 0.76 micron O2 band, which is something that previous work said that the A band, the 0.76 micron band may be more detectable, but I'm finding that the near infrared one actually is. And I'm attributing this to the spectral energy distributions of the host stars, and that they generally emit more photons in the near infrared than they do in the visible. So this is why the 1.27 micron band is more detectable. So yeah, if you were to detect O2 as well as methane in your atmosphere, this would be another biosignature pair. So the ELTs have accessible to them 2 different biosignature pairs, which is pretty important. And then if you were to detect O2 and no methane, you would have no confirmed biosignature pair, at least not this one. So my recommendation here would be to look for indicators of abiotic O2 generation. And the last thing I want to say on this slide is that I tested ozone O3 and I found that it's not detectable at all with the ELTs. And this is just because it doesn't have a lot of high-res structure to detect with the ELTs. So I also looked at water, and I found that water is only accessible for Earth and Archean Earth-like scenarios in about 30 transits or so. And this is at 0.9 microns. Again, the 0.9 micron band was the most detectable one because the SCDs of the host stars peak around 0.9 microns. I did test other bands of water, but I found that this one was the most detectable. Finally, I look at carbon monoxide, and I find that this is only accessible in CO2-rich worlds. And this is pretty important because detecting carbon monoxide can be an indicator that the O2 in the atmosphere came from CO2 photolysis and not from life. CO is a byproduct of CO2 photolysis. So if we detect O2 as well as CO in the atmosphere, this may be an indicator that we're looking at a habitable but uninhabited planet. So one of the final things I want to show you is that I took all of these results and I sort of wrapped them up into this observing protocol. So these are the molecules and the bands that I think we should prioritize in order when these ELTs come online to answer all of those motivating questions that I posed at the beginning of this talk. So first off, I think we should go after carbon dioxide and methane. Both of these are available in about 10 transits or less, and they both give us a lot of information if we were able to detect them both. Like for example, CO2, if we detect CO2, we can answer the question, does it even have an atmosphere, which is a valid question. And then we can ask the question, is the planet terrestrial? And a CO2 detection might help us answer that as well. And then if we were to detect methane as well as CO2, this would be a biosignature disequilibrium pair available pretty cheaply at 10 transits. And then after these first 2 molecules, I think we should go after O2 because, again, it's an important biosignature gas, but it's a little less detectable than CO2 and methane. If we detected O2 and methane, this would be another biosignature pair. So this is why I sort of ranked it 3rd here. And then I think we should go after water because it's important for habitability. It can be an indicator of surface water, but again, it is a little bit more difficult to detect than those first 2 molecules there. And then finally, I have CO on this list. So again, a detection of CO could help strengthen the case for a CO2 photolysis world. But it works for that specific case and doesn't show up in any of these other atmospheres. So that's why I've ranked it last here. So yeah, I'm gonna leave you with my takeaways now. So if you take anything away from this talk, it's that the ELTs can be used to search for more than just O2 in exoplanet atmospheres. All of these other molecules are also available to the ELTs, and we could potentially search for life with just the ELTs. And then here's my observing protocol again. And then I just want to say, check out my paper that came out back in May for more about this and how the ELTs can help us search for life. So thank you, and I'll take any questions.
Thank you very much, Miles. We have time for questions.
Thanks so much for this really cool exploration. I'm curious, so with doing this team, transit observations of planets like TRAPPIST-1, so I kind of event your stellar variability and non-null spots and these sorts of determinations. Could you explain how manipulative those sources of contamination into the approximation. Probably looking at a high evolution, or do you care to figure out what's correct out?
Yeah, that's an interesting question and something I did not consider at all for this work. So we didn't include any type of stellar contamination. And I'm not sure, I'm thinking about it now, and maybe high res could help you in some way to get rid of that stellar contamination. But again, I haven't tested this, and I'm not sure, so I don't want to, say anything about that until I actually test it. But it's on my radar.
I just add that we just give them more money to direct them to look into that for this particular, so we're working on it.
Yeah, one small thing, it hasn't been in other cases, you use the Doppler shift. And in fact, that's good, it's accelerating.
Mhm.
So Earth was pumping out O2 for a long time.
Mhm.
We got to where we are right now. So how do you take into that into account? Because planets can be almost completely dead, or they can be in the Amazon, and somewhere in between.
Right, yeah. So that's an interesting question. Like, for example, we have 21% oxygen in our atmosphere, right? And these other atmospheres that are able to build up some O2 abiotically, those have 6% oxygen in them. So even though those have 6%, it was just as detectable as the 21% oxygen. And that's because we're looking at transmission spectra, which only really get you the top part of the atmosphere. So we're not able to probe all the way down to the surface. So to answer your question, yeah, I'm not sure. We might have to wait for direct imaging to say something about that.
But the 10%,
A tenth of a
was
percent?
for a long time.
Yeah. I'm not sure like what the lower limit on detectability is for O2. That's something that I've been thinking about for a while, and something I want to answer soon. Woody?
You didn't comment on the photolysis that's going on. How well known is that? I would imagine it's going to depend on the spectrum of the star. But can you say a minute's worth on that?
Yeah. So the photolysis that's going on in terms of like water and CO2, is that what you're talking about? Yeah. So I did not personally generate those atmospheres. Those come from other people's atmospheres. So I couldn't comment on the specific photochemistry that's going on there. I just know that it's the dominant source of O2 production in those atmospheres, and it's building up about 6% O2 or so, as well as CO in the CO2 rich atmosphere. So yeah, sorry, I can't answer your photochemistry questions.
Is there a question over here?
Yeah, just regarding the 6% oxygen atmospheres, you said that the sensor can only pick up the top layers. Is that to assume like those atmospheres aren't well mixed, that the bottom you're gonna find something different per se?
Yeah, so O2 is usually well mixed in the atmosphere. If you look at the profiles of our own atmosphere, O2 is pretty straight up and down. But if you were to use direct imaging to probe deeper into the atmosphere, O2 may be more detectable, like lower levels of O2 may be more detectable if you were able to probe deeper in there. Yeah.
All right, well, I have a question.
Yeah.
In your figure, especially with the methane and this carbon dioxide, it looked like it required more transits to detect those molecules as I went to lower mass stars, which seemed a little counterintuitive to me. I don't know maybe put the here if I can make sure I'm not misremembering it. Right, so the darker circles are the N8 co-stars, and they require more transits. Kind of thought that those molecules would be easier to detect around the smaller stars just because of the shrinking radius of the star. Is that photochemistry, or what is going on that's driving that trend?
Yeah,
in
so
stellar mass?
that's just the brightness of the star.
It's just the
Later
brightness of
type
the
hosts
star.
are
So,
you don't get a lot of photons, so it's
Okay.
the spectra are noisier.
So all the stars were at like the same distance, they were
Yeah.
the same brightness.
Exactly.
Okay, got it.
Yeah.
Thank you. All right, time for one or two more questions. If anybody has anything else? Was there any questions online, Lisa? Okay.
There's a beach for, but there's no.
Okay. All right, well then let's thank Miles again for fantastic time. Now going to stage Professor Jim Davenport, who is going to continue the theme, I believe, looking for